Welcome to this problem-solving session. In this video, we will tackle LeetCode problem number 1754, titled Largest Merge of Two Strings. This problem is a fascinating exercise in string manipulation and greedy algorithms, where we aim to construct the lexicographically largest string by merging two given strings. Let's dive in and explore the solution together. In this problem, you're given two strings, word 1 and word 2, and your task is to construct the largest merge of these two strings. A merge is essentially a combination of the two strings, where all characters from both word 1 and word 2 are included exactly once, and the relative order of characters within each string is preserved. However, what makes this problem unique is that we're not just looking for any merge, we're looking for the lexicographically largest one. Lexicographically larger means the resulting string should appear as large as possible in dictionary order. For example, zebra is larger than apple because Z comes after a. Your job is to return this largest merge as a single string. The input strings consist only of lowercase English letters, and their lengths can range from 1 to 10,000 characters. This means the solution needs to handle potentially large inputs efficiently. Let's look at an example to better understand the problem. Suppose word 1 is kaba and word 2 is ka. To create the largest merge, we start by comparing the first characters of both strings. Here, C from word 1 is larger than B from word 2, so we take C and append it to the merge. Now the merge is C, and we continue comparing the remaining characters. Next, A from word 1 is smaller than B from word 2, so we take B and add it to the merge. We repeat this process, always choosing the lexicographically larger character from the current leading positions of the two strings. If the characters are equal, we compare the remainder of the strings to decide. By the time both strings are exhausted, the final merge is kkabaea, which is the largest possible result. Here's another example to clarify the approach. This time, word 1 is abkab and word 2 is ebkaba. We begin by comparing the leading characters, which are both a. When the characters are equal, we look at the remaining substrings. In this case, the next character in word 2 is B, which is greater than the next in word 1. So, we choose A from word 2 and append it to the merge. We continue comparing character by character, always selecting the lexicographically larger option. By following this strategy, the final merge becomes abkabkabkaba. This example highlights the importance of comparing not just the current characters, but also the remaining substrings when necessary, to ensure the result is the largest possible merge. Now, let's consider some edge cases to ensure our approach works for all scenarios. First, if the two strings have completely non-overlapping characters, such as word 1 being AAA and word 2 being ZZZ, the output simply concatenates the two strings in lexicographical order, resulting in ZATSA. Second, if the strings consist of identical characters, like word 1 and word 2 both being AAA, the merge will simply combine them to form AAAAA. Third, if one of the strings is empty, the result will be the other string. For example, if word 1 is ABC and word 2 is empty, the merge is just ABC. Lastly, for very long strings, the solution must handle up to 10,000 characters efficiently by applying the algorithm without unnecessary computations. To implement the solution, we use a greedy algorithm. At each step, we compare the leading characters of word 1 and word 2. If one character is larger, we append it to the merge and remove it from its respective string. If the leading characters are the same, we compare the remaining substrings to decide which character to append next. This ensures that we always make the optimal choice for the largest merge at each step. We repeat this process until both strings are empty. By maintaining this strategy of selecting the lexicographically larger option at every step, we guarantee that the resulting merge is the largest possible string while preserving the relative order of characters from both strings. To solve the problem of constructing the largest merge from two strings, we explored several approaches. First, let's consider the brute force method. The idea here is to generate all possible interleavings of the two strings, ensuring that the relative order of characters in each string remains preserved. Once all interleavings are generated, we simply select the lexicographically largest one as the result. While this approach is conceptually simple and can be implemented using recursion or backtracking, the sheer number of possible interleavings leads to an exponential time complexity of O(2)m plus n, where m and n are the lengths of the input strings. This makes the brute force approach impractical for larger inputs, such as those at the upper constraint of 10,000 characters. Next, we considered a greedy approach. Here, the intuition is to incrementally build the result by always selecting the lexicographically larger character from the current prefixes of the two strings. At each step, we decide whether to take the next character from word 1 or word 2, append it to the result, and remove it from the corresponding string. This approach significantly improves efficiency compared to brute force, but it still has a time complexity of open parenthesis m plus n close parenthesis squared, due to repeated comparisons of the prefixes of the two strings, which can become expensive for very long inputs. The greedy approach, while more efficient than brute force, still has its limitations. The repeated prefix comparisons at each step can slow down the process significantly for long strings. To address this, we refined the strategy into an optimized version of the greedy approach. The key insight here is that the prefix comparison is the bottleneck, so we should aim to reduce the overhead associated with it. Python's string comparison operations are highly efficient and optimized internally, which allows us to avoid manually implementing costly comparisons. By leveraging these built-in operations, we can directly compare the strings without explicitly slicing or generating intermediate substrings, minimizing redundant computations. This optimized implementation retains the same asymptotic complexity of open parenthesis m plus n close parenthesis squared, but performs much better in practice due to the reduced overhead. While this approach is not linear, it strikes a good balance between simplicity and performance, making it a strong candidate for solving this problem efficiently. After carefully considering the constraints of the problem, where the lengths of the strings can go up to 10,000, we chose the optimized greedy approach as the most suitable solution. The brute force approach was ruled out early on due to its exponential time complexity, which makes it infeasible for larger inputs. While the basic greedy approach was a promising alternative, it required refinement to handle the inefficiencies caused by repeated prefix comparisons. The optimized greedy approach stood out because it leverages Python's efficient string comparison operations, which allowed us to bypass the need for manual and costly prefix comparisons. This way, we achieved a solution that is both practical and efficient for the problem's constraints. Additionally, the greedy strategy aligns perfectly with the goal of constructing the lexicographically largest string, as it ensures that each decision made is optimal for the remaining input at every step. The optimized greedy approach was chosen for several reasons. First, it is efficient given the problem's constraints, performing well in practice even though it is not linear. Second, the implementation is straightforward and avoids the complexity of using advanced data structures or recursion, making it easier to understand and maintain. Finally, the approach guarantees optimality as the greedy strategy ensures that the largest possible merge is constructed by making the best local decisions at each step. Overall, this solution balances the trade-offs between computational complexity and real-world performance, making it the most practical and scalable option for solving this problem. In this problem, we are tasked with constructing the largest merge from two strings, word 1 and word 2. A merge is created by interleaving characters from both strings, but we must maintain the relative order of characters within each string. The goal is to maximize the lexicographical order of the resulting string, ensuring it is the largest possible. To achieve this, we use a greedy algorithm. Here's how it works. We start by initializing two pointers, I and j, both set to 0. These pointers will track our current positions in word 1 and word 2 as we build the merge. Additionally, we create an empty list called merge, which will store the characters of the result. Using a list is more efficient than directly concatenating strings repeatedly, as it avoids unnecessary overhead. The next step is to compare the characters at the current positions of the two pointers. While both pointers are still within their respective strings, we compare the substrings starting from I in word 1 and j in word 2. This ensures the comparison considers the remaining portions of each string. If the substring from word 1 is lexicographically larger or equal to that from word 2, we append the character at word 1, I, to the merge and increment the pointer I. Otherwise, we append the character at word 2, j, to the merge and increment j. Once one of the strings is fully traversed, we simply append all remaining characters from the other string to the merge. Finally, we convert the merge list back into a single string and return it as the result. The greedy algorithm works effectively because of the key insight that comparing the substrings word1, I and word2, j at each step ensures we always choose the best possible option to maximize the lexicographical order. Python string comparison is efficient, operating in O, min, len, word1, I, len, word2, j, time, which is suitable for this problem's constraints. We also account for edge cases. For instance, if one string is empty, the result is simply the other string. Additionally, strings with repeated characters, like word1 equals AAA and word2 equals AAA, are handled correctly since the algorithm processes the characters in left to right order, maintaining their relative order within each string. To implement this solution, we use simple and efficient data structures. The merge list is used to store the resulting characters because appending to a list is faster than repeated string concatenation. The two pointers, I and j, allow us to track our positions in word1 and word2 without requiring additional memory. Analyzing the complexity, the time complexity is O, n plus m, where n and m are the lengths of word1 and word2. Each character is processed only once, and substring comparisons, while potentially O, n, in isolation, are efficient overall due to the greedy approach. The space complexity is also O, n plus m, because the only additional memory used is for the merge list, which stores the final merged string. To solidify our understanding, let's walk through an example. Given word1 equals kaba and word2 equals ka, we start by comparing word1, 0, smiley face, equals kaba and word2, 0, smiley face, equals ka. Since kaba is lexicographically greater, we append c to merge, resulting in merge equals c, and increment I to 1. Next, we compare word1, 1, smiley face, equals aba and word2, 0, smiley face, equals ka. This time, ka is larger, so we append b to merge, making merge equals c, b, and increment j to 1. We continue this process, comparing substrings, appending the larger character, and advancing the respective pointer. At the end, when one string is exhausted, we append the remaining characters of the other string. The final result is the string kaba-ea, which is the largest merge of the two input strings. This Python implementation solves the LeetCode problem largest merge of two strings using a greedy algorithm. The function largest merge takes two input strings, word1 and word2, and constructs the lexicographically largest merge by interleaving characters from both strings while maintaining their relative order. The algorithm initializes an empty list merge to store the resulting characters as they are selected. It then enters a while loop that continues until both input strings are empty. Inside the loop, the current states of word1 and word2 are compared lexicographically. If word1 is larger, its first character is added to the merge list, and that character is removed from word1. Otherwise, the first character of word2 is added to merge, and it is removed from word2. This comparison ensures that the largest possible character is always chosen at each step, leading to the lexicographically largest merge. Once all characters from both strings have been processed, the merge list is joined into a single string and returned as the result. The algorithm handles all edge cases, such as when one of the strings becomes empty before the other, since the lexicographical comparison gracefully works even with empty strings. The time complexity is O, n plus m, where n and m are the lengths of word1 and word2, respectively, as each character is processed exactly once. The space complexity is O, n plus m, for the result string. This approach is efficient, concise, and directly addresses the problem requirements, ensuring correctness and optimal performance. This is the Java implementation of the largest merge of two strings problem. The logic mirrors the Python implementation provided, but uses Java-specific features like string builder for efficient string concatenation. String methods such as compareTo and substring are used to handle lexicographic comparisons and substring operations. The solution iteratively builds the largest merge by comparing prefixes of the two input strings and appending the lexicographically larger character to the result. In this example, we start with word1 as cab and word2 as abac, and an empty list merge. The goal is to build the largest lexicographical string by comparing the two strings step by step. First, we compare the entire strings word1 and word2. Since cab is lexicographically greater than abac, we take the first character of word1, which is c, and add it to merge. Now, merge contains c, and word1 is updated to ab while word2 remains unchanged. Next, we compare the updated word1, ab, and word2, abac. This time, ABAC is greater, so we take the first character of word 2, which is a, and append it to merge. Now, merge becomes C, and word 2 is updated to BAC. Continuing the comparisons, we now have word 1 as AB and word 2 as BAC. Since BAC is lexicographically greater than AB, we take the first character of word 2, which is B, and add it to merge. This updates merge to C, B, and word 2 is reduced to AC. Next, comparing word 1, AB, and word 2, AC, AB is smaller, so we take the first character of word 2, which is a, and append it to merge. Now, merges C, B, and word 2 becomes C. Moving forward, C is greater than AB, so we take C from word 2 and add it to merge. This updates merge to C, B, C, and word 2 becomes empty. Finally, since word 2 is empty, we append the remaining word 1, AB, to merge, resulting in C, B, C, B. The final merged string for this example is cabacab. Now, let's consider a second example where word 1 is ABC and word 2 is XYZ. Starting with merge as an empty list, we first compare word 1, ABC, and word 2, XYZ. Since XYZ is lexicographically greater, we take the first character of word 2, which is X, and add it to merge. This updates merge to EX, and word 2 is reduced to YZ. With merge now containing X, we continue comparing the strings. Word 1 remains ABC, while word 2 is YZ. Since YZ is still greater than ABC, we take the first character of word 2, Y, and add it to merge. Now, merge becomes X, Y, and word 2 is updated to Z. Comparing again, Z is greater than ABC, so we take Z from word 2 and add it to merge. At this point, merges X, Y, Z, and word 2 is empty. As word 2 is now empty, we append the remaining word 1, ABC, to merge, resulting in X, Y, Z, B, C. The final merged string for this example is Zyzak. For the third example, both word 1 and word 2 are G. Starting with an empty merge, we compare the two strings. Since G is equal to G, we can choose to take the first character from word 2, which is G, and add it to merge. Now, merge contains G, and word 2 becomes empty. Since word 2 is now empty, we append the remaining word 1, G, to merge, giving us G, G. The final merged string for this example is GG. This approach relies on lexicographical comparisons to ensure the largest possible prefix is added to merge at each step. The greedy strategy we use guarantees that we always build the largest merge. Once one of the strings is empty, we append the remaining characters of the other string to merge. This ensures correctness while maintaining linear runtime complexity, making the solution efficient and robust. To analyze the time complexity of this solution, we start with the outer while loop. This loop continues running until both word 1 and word 2 are empty, meaning its total number of iterations will equal the sum of their lengths, n plus m. Inside the loop, we perform a lexicographical comparison between word 1 and word 2. This comparison, in the worst case, could take time proportional to the length of the shorter string, or o, min, len, word 1, len, word 2. Initially, these lengths are n and m, but they decrease as characters are removed. In the best case, this comparison can terminate early, making it a constant time operation, or O1. Finally, each iteration appends a character to the merge list, which is an O1 operation. These factors collectively contribute to the overall time complexity of the algorithm. When evaluating the total time complexity, the worst-case scenario occurs when the lexicographical comparison takes the maximum time for every iteration. If we sum up the cost of comparisons over all n plus m iterations, we get a series that simplifies to O, open parenthesis n plus m close parenthesis squared, in the worst case. However, in the best case, where comparisons often terminate early, the total cost per iteration becomes constant, or O1, leading to an overall time complexity of O, n plus m. This distinction highlights how the algorithm's performance can vary depending on the input strings, but it is designed to optimize for efficiency under most circumstances. Now let's consider the space complexity. The primary contributor is the merge list, which will eventually hold all the characters from word 1 and word 2, resulting in a size of n plus m. Regarding the slicing operations, while word 1 and word 2, one may seem to create new substrings, the memory used for the discarded portions is effectively reused, meaning these operations do not add to the space complexity. No additional data structures are introduced, so the auxiliary space required is O(1). Therefore, the total space complexity is determined by the size of the merge list, which is O, n plus m. Compared to a brute force approach that generates all possible interleavings, resulting in exponential complexity, this optimized method significantly reduces both time and space requirements. To summarize, the algorithm has a best-case time complexity of O, n plus m, and a worst-case time complexity of O, open parenthesis n plus m close parenthesis squared. The space complexity is O, n plus m, driven by the size of the merge list. This approach effectively balances efficiency and simplicity, avoiding the exponential blowup of a brute force method by using a greedy strategy to build the largest merge step by step. One common mistake when solving this problem is using a greedy approach without a proper tie-breaking mechanism. For example, if you encounter two equal characters from word 1 and word 2, simply appending one without considering the lexicographical order of the remaining substrings can lead to a suboptimal result. It's important to compare the remainder of both strings and prioritize the one that results in the lexicographically largest merge. Another issue occurs when attempting to modify strings directly during iteration. Since strings are immutable in most programming languages like Python, this approach can lead to inefficiencies due to repeated concatenation or slicing, which increases runtime complexity. Finally, many people overlook the termination condition. If one string is completely processed before the other, the remaining characters of the unprocessed string must still be appended to the merge. Neglecting this step results in an incomplete merge and incorrect output. Another pitfall is using plain recursion without memoization. While recursion may seem straightforward, it can lead to an exponential number of function calls, especially when exploring all possible merges, resulting in a time complexity of O(2) n plus m. This becomes impractical for large inputs. Memoization is crucial to store results of overlapping subproblems and improve efficiency. Additionally, misunderstanding the problem constraints is a common issue. Some assume that word 1 and word 2 must be of equal length or fail to consider edge cases like one string being empty. Misinterpreting constraints can lead to runtime errors or incorrect outputs. Always review the problem statement carefully to ensure your solution accounts for all possible scenarios. This problem highlights a key pattern often seen in greedy algorithms: lexicographical comparison of substrings. Recognizing and mastering this pattern is valuable for solving similar problems. The optimal solution involves a two-pointer technique where you compare the current characters of word 1 and word 2. In tie-breaking situations, you compare the substrings starting from the current positions of the pointers. This ensures a time complexity of O, n plus m, which is efficient. During interviews, it's important to clearly explain the rationale behind your greedy choices, why taking the larger character or comparing substrings leads to the optimal solution. Also, make sure to test edge cases like empty strings, repeated characters, or very large inputs to demonstrate that your solution is robust and handles all scenarios correctly. If you want to strengthen your understanding of this problem, it's helpful to explore related problems that use similar techniques. For instance, LeetCode 402, remove k digits, is another greedy problem where you construct the smallest number by removing digits. LeetCode 316, remove duplicate letters, focuses on constructing the smallest lexicographical string with unique characters. LeetCode 1405, longest happy string, involves constructing a string under specific constraints, again using a greedy approach. Lastly, LeetCode 321, create maximum number, is a more advanced variation that requires merging two arrays to form the largest number. Studying these problems will reinforce the greedy algorithm pattern and help you apply it in different contexts. There are several alternative approaches to solving this problem, each with its own trade-offs. A recursive approach with memoization involves exploring all possible merges while storing results of overlapping subproblems. This method is easier to implement but tends to be slower due to function call overhead. An iterative greedy approach, on the other hand, uses two pointers to compare characters or substrings and build the merge directly. This technique is faster and more space efficient but requires careful handling of edge cases to avoid bugs. Lastly, a heap-based approach involves maintaining a priority queue to always select the lexicographically largest character. While this is an interesting method, it's not optimal for this problem due to its O, n log n, complexity. However, it may be useful in solving certain variations. Understanding these methods and their trade-offs can help you adapt to different problem requirements effectively. Great job! To summarize, we tackled the challenge of constructing a lexicographically largest merge using a greedy approach. We walked through the time and space complexities, key takeaways, and when to apply this technique. Thanks for tuning in. Don't forget to like, subscribe, and stay tuned for more helpful solutions. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!